check out this apple I'm holding. Right now I'm holding it really still, so it has no kinetic energy. However, it's a certain height above the reference point, which let's say is the ground. So it definitely has gravitational potential energy. Now watch, when I let go, all that gravitational potential energy decreases, but it gets converted or transformed into kinetic energy. In this lesson, we're going to look more deeply into gravitational potential energy. Alright, put yourself in this situation. You are hiking and you're about to walk past several mountains. And there's more than one route that you can take. Now there's a nearby mountain that has a heavy boulder at the top's edge. You know that this boulder is unstable and it might fall down. On the other hand, there's a nearby mountain as well. This one only has a few pebbles at the edge. They're also unstable and they can also fall down. Now, just gut instinct, which mountain would you feel safer walking down below? You guessed right, you'd probably feel safer walking under the mountain that has the pebbles on the edge. Yes, pebbles hurt you when they fall down, and yes, maybe the pebbles are equally as high as the boulder. But the only distinction between the boulder and those pebbles is the mass. The boulders have a much greater mass, and according to the potential energy formula, the higher the height and the greater the mass, the greater the potential energy. On Earth, the gravitational constant is the same. In the given formula, PE equals mgh, PE stands for potential energy, M stands for the mass in kilograms, units are really important here. G is the gravitational constant, 9.8 newtons over kilograms or meters over second squared, and H is the height in meters. The energy transferred can be calculated as work. Now in the situation of a gravitational potential energy, if you are climbing vertically up, just vertically up, you're not moving at a certain angle, then the gravitational potential energy in this case will equal as well to the work. The gravitational potential energy is unaffected by the angle at which the object is rising or falling. You just measure vertical. However, when there is an angle, then you have to calculate the mechanical work using the formula work equals force times distance. Now to clarify, the force that we're referring to is the effective force. This effective force is the force that is in the direction of movement. So if the object has a force F applied at an angle theta, then the effective force would be F cos theta. Now think a moment about inclined planes. In your real day-to-day life, if given a choice, would you rather carry a couch up a flight of stairs? Or would you rather push it up on an inclined plane, put some sort of wooden ramp on the stairs and then drag the couch onto it? What would you pick? You'd probably opt to use an inclined plane. The thing about inclined planes, what's really great about them is that yes, sometimes you may need to go over a longer distance to move your object, however, there is less force required. So you see that bowling ball, if we were going to push it directly from the bottom straight up 2 meters, that would require more force than if we just simply dragged it across a 4-meter long ramp. In the real world, not everything moves on a frictionless surface. You need to take friction into account. Now, as we know, if there is friction on a surface, to move an object will require a bit more force. And the reason that has to happen is because you need to overcome the frictional force first. The work that is used up just to overcome friction is converted into something called heat. Yes, heat is a form of energy. To calculate the heat, you need to find the force necessary to overcome friction and then just multiply it by the distance. Again, work equals force times distance. That's all for now. See you next time.